this is Gururaj and here is my video on Parallel Axis Theorem. Well, let's get started with a small experiment. Okay, here is a solid object and I have fixed some axis on this. This is the axis that goes through the center of mass, mostly through the center of mass, and here are the axes that are parallel to this. Okay, so here this axis is parallel to the axis passing through the center of mass. This axis is also almost parallel to the center of mass. What I'd like to know from this experiment is when I try to rotate it through these axes, which axis will give me the least resistance? Well, let's get started. Okay, so I rotate it with the center of mass and I'm feeling certain amount of resistance. Now I try to rotate it with this axis and I am feeling a little more resistance. And when I try to rotate it with this, again I'm feeling a little more resistance. Okay, so this means that the resistance offered by the center of mass to the rotation by the axis passing through the center of mass was the least. Okay, so I can just make a note here that moment of inertia through the center of mass is the minimum value offered by a body, minimum resistance offered by a body to rotation. Okay, so ICOM is a moment of inertia through center of mass. So what about the other axis then? Okay, can I write anything about these two axes? That they also offered a resistance, but that resistance was greater than the resistance offered by the center of mass. And to clarify, these axes need not be only on the body of this object or any object. We can also have a situation like this, wherein the center of mass is passing right through this point and the axis of rotation is somewhere far away from the body. And when I try to rotate with this as the axis of rotation, again I will feel some kind of a resistance. And that resistance will be far greater than the axis that I have put inside the body. Okay, but yeah, is it applicable only to the sphere or only to a ball? No, this can be replicated to any object. Okay, fine. So the resistance offered by a parallel axis, the moment of inertia of a parallel axis to the center of mass will be equal to how much? It is greater than ICOM. Okay, so I'll just write ICOM plus something. How much is that something? Well, this will be answered by a thought experiment and through this theorem. Okay, fine. So to go ahead and find out as to how much is this or determine how much is this value, this something, let's quickly summarize as to what we just discussed. Here is the solid sphere and here is the axis of rotation passing through its center of mass, and we have a value for this ICOM. You might know that for a sphere, solid sphere, the value is okay, sorry, not 5 by 2, it is 2 by 5. Okay, 2 by 5 m r square. But what is m and what is r? M is the mass of the object, r is the radius of the object or the radius of the sphere in this case. Okay, now this was one part of the experiment. The other part of the experiment was the same sphere. Here is the axis passing through the center of mass, but the rotation axis was located somewhere else. Okay, the distance between the rotation axis and the center of mass axis, let it be h. The variables remain same, m and r. So we get a moment of inertia here as well, okay, which is greater than the moment of inertia of ICOM. So ICOM plus something. Now comes the question of thought experiment, right? Till here it is just what we did till now. Okay, fine. So what is this thought experiment? Consider a particle mass. Okay, what is the mass of this? This is m. But what is a particle mass? Well, a particle mass is something that does not have a length, does not have a breadth. It is just a point in space wherein there is some mass. Okay, in this case it is m. Now let's try to rotate this particle mass through this axis. Okay, this is the axis of rotation. Okay, and here was the axis of rotation. Okay, now here is the axis of rotation. Now what will be the moment of inertia offered by this particle mass? Okay, the I value will be equal to m into r square. But what is r here? R is the distance of this mass with respect to an axis. This we have learnt earlier, correct? So here the distance is 0, therefore the moment of inertia is also equal to 0. You might be thinking that we just told ICOM is the minimum resistance, but here we are getting I value to be equal to 0, isn't it? Then isn't this the minimum resistance? Actually, it is not to be confused with minimum value. This means to say the particle will not be able to rotate. Okay, so why it will not be able to rotate through axis passing through its center of mass is something that we can reserve it for another day. But however, this does not mean it's a minimum value. Now we have taken a particle here, so let's take the particle here as well. And instead of axis passing right through it, let's create an axis of rotation for the particle mass at a distance h. So what will be the value of moment of inertia in this case? Applying the same formula, yeah, the mass is em, so applying the same formula, we will get, 1 second, just need some distance, yeah, I is equal to m multiplied by h square. Okay, so this will be the moment of inertia offered by the particle mass. Now comes some thinking to do. What is the thinking? What if this particle mass explodes into a sphere? And what will be the radius of the sphere? Yes, you guessed it right, it will be r. So it became a solid sphere. It is not a particle mass anymore, and this point will be its center of mass. Okay, so mr. Then the situation becomes the same. Now this will end up offering some inertia, isn't it? Experiment proves it, formulas prove it, that a sphere that with the mass and radius, you try to rotate it through its center, it will not be a 0, it will be equal to the center of mass inertia. Okay, so I is not 0 anymore. We need to include, as this exploded, we need to include the ICOM. Okay, fine. So if we can explode this particle, then we can explode this particle as well, right? And the same conditions. It becomes a sphere of radius r with mass m. This point is no longer a particle mass. It is the instead center of mass of the sphere. So now this situation and this situation are same, identical. Okay, but what about its inertia then? Because this exploded into a sphere, because this point exploded into a sphere, we had to include the ICOM as well, the additional inertia, okay, which the particle mass did not have. So here in this case also we will have to include the ICOM. Okay, if it is present here, then it cannot be that it is not present here, it is also present here. So now what we have is two identical situations, two formulas, both can be equated. When we equate, we get the value for this something as equal to mh square, isn't it? ICOM and ICOM are the same, so here we go. IPA, that is the moment of inertia through a parallel axis, will be equal to ICOM, that is moment of inertia through the center of mass, plus mh square. Okay, what is h here? Distance between the two axes. This axis is parallel to this axis. Fine. So this is the famous formula that you'll find in the textbooks and in various study materials, including videos. Okay. So now the question is, whether do you agree with this? Okay. Or think about this. What if we could make this collapse into a point particle mass? Can I collapse this into a particle mass, and then will the results be interchangeable? Is something you can think about. Okay, are there other methods of determining moment of inertia for a parallel axis? Yes, integration provides a tool for finding out or determining moment of inertia for everything. But here I've presented you with something to think about. So until you keep thinking, I'll keep thinking about one more video. So until next time, take care. Thank you.